All right. So we are going to go ahead and start our next unit here. This is chapter 6 from our textbook. Like many people, John Muir wishes that he could get a really good bowl of ice cream out in the middle of the wilderness. Obviously spent a lot of time hiking out there, and
Is it cold in the winter?
in the summer, you know, does he look like he's in the snow? And where there's demand, of course, there must be somebody to fill that demand. So,
That's me. When I get old.
what we want to be able to do is we want to be able to make some ice cream out in the wilderness because there's a good business opportunity there. We can make some money, okay? And provide a valuable service to hungry hikers.
I'm pretty sure there aren't many.
Trust me, most of the hikers are hungry. So, the key to making the ice cream, we can get the milk out there, you know, we can raise yaks or whatever and have yak milk. We could grow beets and make the sugar from the beets, and that's pretty much all we need to make ice cream, okay? Maybe we can grow some vanilla orchids or something if we really want to have some vanilla beans. The key to making ice cream work out in the wilderness, and we're talking about in the summer, no snow around, okay? We need to be able to control the energy. We need to be able to remove heat from our ice cream mixture, okay? So we've got the perfect mixture. We can freeze this up. We want to turn this mixture of liquid, okay, into frozen ice cream, okay? We can get the dipping dots. That would obviously be awesome. Let's see what happens. We need to remove heat from this mixture. We use the symbol Q to represent heat. That is indeed how they make dipping dots. Liquid nitrogen. Yeah, it's true. They're very cold. Liquid nitrogen. So yeah, maybe we can get some liquid nitrogen. The key here, though, is that we need to be able to pull the heat out of this mixture. Okay? So what we want to do is we want to start to understand heat. What is heat flow? What causes heat to move from one place to another? How can we measure it? How can we control it? That's the key to making good ice cream. Okay? So to do that, to look at this change in energy, our heat, we need to broaden it out a little bit first. Okay, then we'll sort of look at heat by and large. But there are two parts to this total change in energy that we want to look at. One of them is work, and the other is the heat flow. Okay, together, the amount of heat that moves from one place to another, okay, heat flow is a kinetic energy movement, and then work done together are going to combine to give us the total change in energy. We use capital E to represent energy in its broadest sense, and the delta, of course, means change in. So what we're thinking about is we're thinking about two aspects. We have heat, which we have a pretty good idea, has to do with temperature changes. It's a measure of sort of random thermal kinetic energy. And then work is a little bit more tricky term. For our purposes, work is pretty much going to be defined as a change in volume at constant pressure. So if we were to imagine take this cylinder and start here and compress it down, okay, so the particles are all bouncing around inside there. We changed the volume of this container, okay, at some pressure, okay? We'll deal with the pressure in a bit. The pressure might change if we didn't hold the temperature constant. Or, you know, if we allow the temperature to change, then the pressure might stay the same. So we can deal with that. So here we have a change in volume at some pressure. Okay, and let's assume right now that we're at constant pressure, which would assume some change in the number of particles or the temperature most likely. So we'll ignore that for a sec. If this quantity is equal to the negative amount of work done by the system, okay? So it's the same magnitude but opposite in sign. Positive and a negative here is really important because the positive and negative in this energy stuff for Q, for W and these things, positive and negatives tell us whether energy is going into the system or out of the system, okay? And so we want to talk about, we use some words to describe energy in versus energy out. We mathematically will look at that based on these signs, the signs of the values. So the sign tells us direction, and then the value, the number, tells us magnitude. So we have some words, English words or Latin words, that we use to do these things. Exothermic, exo like exoskeleton, out, thermic energy, okay, or heat. So exothermic means that energy is lost by the system, and the sign change will be negative. Means that our system, the thing we're interested in, is going to lose energy. That's an exothermic change. So, in our case, the system is our stuff, our mixture. That's our system. And we're talking about it losing energy. That could be us pulling energy out of it, losing energy to the surroundings. What are the surroundings? The surroundings are everything else in the universe. Okay? So we talk about a system, the thing we're interested in, the thing we're studying, and the surroundings as everything else. So what we're interested in is energy, in this case energy coming out of the system into the surroundings. We call that an exothermic change. Okay? So exothermic, energy being lost from the system to the surroundings, and the sign for Q, the value, if we had the value for Q, it would be a negative value, because it would be indicating that energy is being lost from our system. So that it starts at an energy value up here, and it ends up at an energy value down here at some arbitrary scale. It decreased. The change was a negative value. The amount of energy in the system went down, got smaller. Okay? Endothermic, on the other hand, is the opposite of this. Okay? And endothermic means that the system gains energy, and that its sign change will be positive. Okay? In this example, okay, where we compress like this, what we're having happen here is our system, okay, gained energy from the surroundings. We had to do work on the system. Our volume change was negative. The volume got smaller. Okay? So that means that the system, in compressing this, in pushing that plunger down, work was done on the system. Energy went into the system in the form of work, in the form of compressing that thing. So the value for the work would be positive. Because the volume change was negative, the two negatives would make a positive value for our work.
So for exothermic, work is negative.
So yeah, we can talk about exothermic, the work value would be negative.
So on the paper you have work defined as force acting over distance. But you told us that it was like
Yep.
change in volume and constant pressure. Is that?
So the pressure is the force, and the change in volume is equivalent to the distance. But work in its most generically defined value is force multiplied by distance. So if I lift the remote up, that I did work. Both up and down, I do work. But if I hold it like this and I walk sideways, I essentially do, in a perfect world, no work on the remote. Because the distance was orthogonal at 90 degrees to the force I'm applying. I'm applying a force up to hold it in place, but I'm moving at 90-degree angle to it. So that takes no work to do. Work is defined in this very particular way. Now that's not to say that my muscles didn't burn energy and do stuff, but they didn't do work in this very technical physics definition, which is not super important for us.
What sign would Q in this one?
We don't have information about what's happening with Q. If the temperature remains constant, then Q could be 0. Temperature needs to change for Q value to change. So, work is not something that we're going to spend a lot of time talking about. In fact, that's pretty much it. Mostly what we're interested in is how can we move the heat around? How can we remove heat? Okay? And how much heat do we have to do? So how do we measure heat? Okay? And we know that temperature is definitely going to be a factor here. Right? Temperature is a measure of kinetic energy, a direct measure of kinetic energy. Heat is kinetic energy. So that's definitely going to be a factor. The other thing that's going to be pretty important here is how much. How much ice cream am I trying to cool down? The more liquid I have, the more energy I'll need to remove. Because the energy is going to be on a like per mass basis, on a per how much I have. It's going to depend on it. So, temperature and mass are clearly going to be important here. But there's another aspect to this that we have to keep in mind. Different substances respond to energy in different ways. Not all substances change their temperature the same amount for a given amount of energy. We have to have another variable in here that we call the specific heat. So if I'm thinking about removing energy from my ice cream, the amount of energy I need to remove depends on how much ice cream do I have? How much ice cream am I trying to make? What mass of liquid do I have? It depends on how much energy does it take to change the mass, to change the temperature of the mass, I should say. So S, sometimes we see this as a C, but S, our specific heat, is the amount of energy it takes to change 1 gram of the substance 1 degree Celsius. So joules is our unit of energy, G is grams, and C are degrees Celsius. So how much energy does it take to change 1 gram of the substance 1 degree Celsius? So there are ways that we can go in the lab and figure it out, or this is values that we can look up in tables, and they can be given to us in a problem. So it's something we have to figure, but it's all measured empirically. So the values we're going to have are going to be values that we go in the lab and figure out, or are given to us based on other people going in the lab and figuring it out. And we will actually do that. We're going to figure out the specific heat capacity of some substances in a lab that we'll do. And finally, the change in the temperature. So Q equals ms delta T. Delta, remember, is our change in temperature. So if we want to make 250 grams of ice cream is mostly water. Water has a specific heat capacity of 4.18 joules per gram degree Celsius. That is, it takes 4.18 joules to change the temperature of 1 gram of water 1 degree Celsius. And if it's at, say, 25 degrees Celsius to start with, and I need to cool it down to 0, that means my change in temperature is negative 25 degrees. It's always final temperature minus initial temperature. A change, a delta, is final minus initial. So I can substitute these in, 250 times 4.18 times negative 25. And I can calculate that I need to remove, that's what this negative sign tells me. How much energy do I have to remove? Energy lost. I need to remove 26,125 joules, about 26 kilojoules.
How would you remove that?
We'll get there. It's the next slide. So, a couple of things to note. There are other older units that I'm sure you have all heard of called calories. Okay? So calories are units that we see all the time in the United States on food packaging and stuff like that. If you go to Europe, all that stuff is listed in joules or kilojoules. The food calories that we see on our packaging are all kilocalories. Okay, so a food calorie is 1,000 calories. And 1 calorie is equal to 4.18 joules.
Oh, so it's based on water.
It's all based on water. Exactly right. So, a food calorie is the amount of energy it takes to raise 4 liters of water 1 degree Celsius. Or you can think of it, the amount of energy it takes to raise 1 milliliter of water 4,000 degrees. It's a lot of energy. Right? A food calorie is actually quite a bit of stored energy. 4 liters to raise 4 liters of water 1 degree Celsius, or to raise 1 milliliter of water 4,000 degrees. 4,000 degrees Celsius. That's not very much water. All right. So, Jonathan's question is a good one. How can we remove the heat from this solution? What's one thing that I could do to cool it off? Put it in the freezer. I'm out in the woods. I don't have a freezer. Put it in the snow or put it in contact with something cold. Okay? So if let's say I'm up in the woods, but there's no snow. So I need to bring cold things up, probably by pack mule or something, wrapped in insulation. I'm going to bring cold things up. So what if I brought like a cold piece of metal? That's cold. It absorbs heat really well. They're good conductors. So if I had a cold piece of copper, let's say I had a chunk of copper metal, I could bring it up, stick it in my solution. It would warm up, drawing energy, drawing heat from the solution until they reach a thermal equilibrium. And that would cool the solution down by absorbing heat from it.
You have copper in your ice cream.
Well, it's a big chunk. I can pull it out later. Besides, a little bit of copper, it's good for the customer.
Really?
So, this process of measuring how this takes place, of measuring how much energy, is frequently called coffee cup calorimetry. Calorimetry is the word that we use in terms of measuring heat, measuring calories. And coffee cup calorimetry gathers its name because the key component is a coffee cup. Styrofoam coffee cups turn out to be really good insulators, certainly for our purposes. Styrofoam is an excellent insulator. And we want to isolate our system from the surroundings. We don't want any excess energy to go in or out from the air around it. So if we can minimize that, it will give us more accurate results.
But wouldn't if the sample is warmer than the atmospheric temperature, so wouldn't already that be interacting? So.
Well, that's what the coffee cup helps minimize.
But it still wouldn't.
It wouldn't eliminate it, but if I can slow it down, enough, coffee cup and a styrofoam cup, coffee will stay warm for a pretty good amount of time. That's telling us that not a lot of heat is leaking out. And so that means that we're isolating our system from the surroundings. And so our system is going to be 100 grams of water. So we're going to start with 100 grams of water. Our solution, our ice cream solution, is mostly water. For our introductory start here, we're just going to assume that it's water and that it will behave basically like water, which is pretty close. So we have 100 grams of water. What we want to do is we want to measure the temperature of that. So we stick it into the water, and we can find out that it has an initial temperature or starting temperature of 25 degrees Celsius. So we are going to want to cool it down. But right now, what we sort of need to figure out is what happens when I put a piece of copper into the water. How much energy can the copper absorb? What is the copper's specific heat capacity? Remember, the specific heat capacity is a measure of how much does the temperature change for a given amount of energy. So if we have a chunk of copper, say 200 grams, and we've got it nice and cold, we've brought it out of a deep freeze commercial freezer, it's at negative 50 degrees Celsius. Okay, and you can get a freezer that will cool things to that. Your home freezer gets pretty 10 or 15 degrees below zero. So a nice commercial, a high-powered commercial freezer can easily do this for us. Huh? Well, yeah, we'll have to see. There might be better options. But this is our first idea. This is our first point we're looking at here. So let's take this 200 grams of copper and dump it into the water. Okay? When that happens, when we do that, we wait and we watch the temperature. We record the temperature every 30 seconds or 10 seconds or whatever. The lowest point that the water reaches is 15.3 degrees Celsius. Now, where did the energy from the water go? Went into the copper. Okay? So the copper started at negative 50 and went up to 15.3. How do I know that the copper ended up at 15.3? They're in equilibrium. They're touching each other. They're in thermal equilibrium. Okay? So the energy of the copper has to be equal to the energy of the water. But we need to think carefully here because remember we said the signs tell us which way is the energy going. So they can't both have the same sign. Which one gained energy? So the sign for this would be, it's going to come out positive, and the sign for the water should come out negative. Okay? So here's what we want to do. Let's calculate this. Q for the water. 100 grams of water, 4.18 joules per gram degree Celsius. That's the specific heat capacity of water. Okay? Specific heat capacity of water. The change in the temperature, 15.3 minus 25. Now we can set up an equation for the copper, but there's a problem. Right? We don't know what the specific heat capacity of the copper is. That's really what we're trying to find out, because it will tell us how efficient is the copper, how much copper do I need to be able to get a specific amount of temperature change, or amount of energy absorbed. So, the same, yeah, exactly right. I know that because I put these together, that the energy of the copper has to be equal to the energy of the water, but opposite in sign.
So instead of it being times 4,
So I put that negative here. That's what's going to take care of the sign for me. Okay, this negative here is whatever the value, the sign, whatever this value for the copper is, change its sign. Now it's equal to the water. The energy lost by the water is gained by the copper. This is one of the key things in doing calorimetry, that the energy lost by one part is gained by the other. Okay, the energy doesn't appear or disappear. If you lost energy, it had to go someplace. And our assumption is that the energy gained or lost by the water is equal to the energy lost or gained by the copper. Yes, there's going to be inefficiencies. There's going to be some going to the surroundings. The better our insulation, the lower that is. That lower error there will be in our measurements. So we can go ahead and substitute these two equations in. Here is our value for copper. Here is our value for the water. Now we're in math. Okay? Solve for S. So we're going to go ahead and we can go ahead and do that. We can solve for S. We can start to turn these values. Don't forget your extra negative sign here. Right? We had to put that extra negative sign in. So I just stuck a negative sign here because these are all multiplied. Now I can go ahead and do this. Okay? I'm going to go ahead and convert. This is, add these numbers, multiply by 200. This is all this times that. Subtract those, get some numbers. Question?
Why? Oh, is it only -200 because they're all multiplied?
Because they're all multiplied. If you wanted to put a parentheses around this whole thing, that would achieve the exact same effect. But I just put a negative on one of them because they're all multiplied by each other. So that works. Notice I put the parentheses in here on this addition thing. So I can divide this out, and I'm going to get that the specific heat capacity of copper is 0.310. So I can use this process to go through and determine specific heat capacities of lots of different substances. Okay, I can go through and determine the specific heat capacity of different substances. As long as I know one specific heat capacity of water, in this case, which is the one we usually use, I can dump other things into it and see how the temperature changes and know that the energy lost or gained by my unknown went into the water. As long as I can measure the temperature change of the water, I'm good to go. So, what does this tell me about the copper? How much energy does it take to raise 1 gram of copper 1 degree Celsius? 0.31 joules. In other words, a 1 degree temperature change of the copper, okay, takes a lot less energy than a 1 degree temperature change of the water. Our water takes about, 12 times more energy to change than the copper does. Okay? Copper is a very good conductor, it will move energy very quickly because of a number of reasons. But one of them is it changes temperature very quickly because its specific heat capacity is very low. Okay? It takes only a little bit of energy to raise the temperature.
What determines the specific?
Specific heat capacity is actually fairly complex in terms of why it is what it is. A lot of it has to do with the internal structure of the things, how it's bonded together, how the electrons are shared between the atoms in the molecule or solid or whatever it is. Pretty complex stuff in terms of actually doing it. You can actually go through and calculate it. It is possible to do from just some initial math equations and things like that. But this is very complicated calculus. Most of this is done in a way like this where it's actually measured, where we go ahead and measure it in the lab. We'll go through and do an experiment like this. Okay? The key to doing these problems is this realization, that the energy lost by one part is the energy gained by the other, and that you can set these equations equal to each other as long as you change the sign of one of them. So you stick an extra negative in. It doesn't matter where you put the negative, okay, because it will come out either way. Because otherwise you'll have an extra negative sign and they wouldn't be equal to each other, right? When we calculated for the water, it came out as negative 4,000. If you do a calculation for the copper, it would have come out positive, but we stuck a negative sign on here. And so once we know the specific heat, now we could say, oh, if we plug it back in, then the two sides are equal. That's the whole purpose. Okay? All right. One thing we want to be able to do, and your homework is going to ask you to do this, and I'll ask you to think about this question. How much copper would we need to cool 100 grams of our solution? Okay, that's a question that you should be able to answer. So what we started, remember our sort of initial idea here was that we're at 25 degrees and we want to cool it down to 0. Okay, so that was our ice cream out in the woods. We had 25, let's say we had just 100 grams of it, and we wanted to cool it from 25 down to 0. Could you calculate how much copper you would need? You have the specific heat of water. You now have the specific heat of copper. Assume the copper is at, again, negative 50. So you can have the temperature change of the copper. That's a solvable problem. And there are problems like that for you to do tonight for homework. Questions?
So the problem we just did, the 0.10, that's the specific heat capacity of copper.
That's the specific heat capacity of copper. That's what we calculated in that last problem.
Those like just those like those standards, or is that like just general? It's always copper.
That's for copper.
So it's like
Just copper.
never.
Never is a very dangerous word.
Or it doesn't change.
Technically, specific heat capacity does fluctuate with temperature, but
Drastic.
not enough for us to worry about.
Okay. Are we doing water? How do we know?
So if you assume that our solution is water, that our ice cream solution is water, that's the assumption we're making for right now, for this unit. You can go ahead and do it if you want, or you can start working on your homework. It's okay, either way. I want you to realize, to think about, could you do this? You need to be able to. These problems will show you how, or I'll ask you to do that kind of thing.